So we ended the last video with this question: the rate of disappearance of a reactant decreases with time, increases with time, stays the same throughout the reaction with time. And hopefully what you got out of that was that as the reaction, so if this, let's say I have a simple reaction, A goes to B. If this is the concentration of my reactant, A, and this is time that the reaction takes place, we start with a higher concentration. So this would be the concentration of our reactant at time 1. Now, as the reaction goes, the rate of the reaction will be fastest when the concentration is highest, and as it proceeds over time, less and less of the reactant is available to react, and so the curve of the reaction, which is a change in concentration, the change in the concentration of our reactant with respect to the change in time, that curve represents, as it flattens, a slower and slower change in concentration over time. And so, yes, A was the answer to that question. All right, and remember, this is a reactant. And so initially, we would have a negative sign out here. What is the negative sign? It simply means that reactants disappear as the reaction moves forward. And the reason that we actually come out with a positive result is because that change is always going to be measured reactant concentration at time 2. That's down here where the reactant concentration is a lower value minus the concentration of A at time 1. That's the initial concentration when it's higher. And so this is a smaller number minus a larger number. That gives us a negative number. And so because we say reactants disappear, we wind up with a negative times a negative, which gives us a positive value. And remember that you always report reaction rates to the positive. Okay, so let's examine the way a reaction slows down quantitatively as a reaction proceeds. And so this is just describing the rate of disappearance of hydrogen ion measured for the following reaction, and the following data were collected. So this is a real-world scenario of actual data that might have been collected from this reaction. And what we're going to measure is the concentration of hydrogen ion as it changes over time. You might remember from Chem 1 that HCl, hydrochloric acid, is one of your 7 strong acids. It's a strong electrolyte, so it dissociates virtually completely. And we can measure quite easily the concentration of hydrogen ion by measuring what we call the pH of the solution, which is the negative log of the hydrogen ion. And we'll get to that later on in the course, not too long from now. But here is the graph that we're talking about, and at time 0, that's where the hydrogen ion concentration the reaction hasn't started yet, so it's going to be at its highest concentration. So we would call this H plus in brackets 1, the initial concentration, and then the reaction starts. And what's happening is the hydrogen ion is reacting with the oxygen on the methanol and adding to it the hydroxide and or hydroxyl group, and the hydrogen ion are making water, and then the chloride ion will glom on to the methyl group here and make the chloromethane. So we can measure the rate of the reaction by simply focusing on the hydrogen ion concentration as it changes over time. So we're going to pick, first of all, these 2 periods of time, and we're going to measure the average rate of disappearance of the hydrogen ion. Okay, and so all we have to do is use our formula, which is going to be the change in concentration of h plus with respect to the change in time. And because this is a rate of disappearance, it's going to be a negative sign here. And up here we'll have the time 2 hydrogen ion concentration of 1.67 molar minus the initial concentration of 1.85 molar. And so when we do that and then we divide by time 2, which is 79.0 minutes minus 0 minutes, that's our starting time. So when we do that calculation, we get a rate, an average rate between these two concentrations, between 79 minutes and 0 minutes, the initial time, of 2.28 times 10 to the minus 3 molar per minute. Now what we want to do is we want to examine the rate at a later point in time. And so this is now T1, 316 minutes. This is now T2, 1.30. That's going to be the concentration of H plus at time 1. 1 molar will be the concentration of H plus at time 2. We're going to do exactly the same concentration, the change in concentration of H plus with respect to the change in time. This is the disappearance of a reactant. So we have a minus sign. Remember, all that minus sign means is reactants disappear. Ultimately, we have to come out with a positive rate. So our H plus concentration at times 2 is 1.00 minus our H plus concentration at time 1, which is the higher concentration. That's going to give us a negative 0.30 molar. We'll divide by T2, and T2 is 632 minus T1, which is now 316 minutes. And when we do that, we wind up with 316 minutes for our delta T. Because we've got a negative sign out here, you have a negative times a negative, which gives you a positive value. And you wind up with 9.49 times 10 to the minus 4 molars per minute. 9.49 times 10 to the minus 4 molar per minute. And as you can see, the reaction has slowed down. And this is the average rate of the reaction. What we're going to examine now is the difference between an average rate of a reaction and what we call the instantaneous rate of a reaction. So let's do some simple rate comparisons. First, we have the average rate. The average rate is determined by simply 2 points of time on a curve. That is exactly what we just did. So in this previous slide, when you look at that curve, we took 2 points on the curve. We do a straight line between them. Okay, I apologize. That doesn't look very straight, but you know what I mean. And we calculated the slope of the line, or the difference between those 2 points. This is analogous. The average rate is analogous to you getting in your car, noting your mileage on your odometer, noting the time, and then driving home, pulling up in your driveway at home, noting the mileage, knowing the time, and simply calculating the difference. So you get the mileage divided by the difference in your time. So you wind up with the time in the denominator. That's an average rate. It doesn't tell you how fast you were going at any particular point in the trip. That would be the instantaneous rate. The instantaneous rate is determined at a point on a curve. It tells you what's happening at that point, not what happened before or after in that particular reaction. So this would be analogous to you driving down the road and looking at your speedometer and seeing how fast you're going at that particular moment in your trip. You might be stopped at a stoplight. You might be doing 65 down the highway. So an average rate 2 points on a curve, and you simply calculate the slope on the line or the difference between the 2 points on the curve. The line intersects the curve at 2 points. The slope gives you the average rate over some interval of time. And as I said, that's what we just did. Now let's do the instantaneous rate. So here is that same curve. Not a lot of curve, but there's some. But we're going to go ahead and we're going to calculate the instantaneous rate at some point on the curve. So in this particular case, your point would be at 300 seconds or 300 minutes. That would be the particular point, and you would simply draw a tangent to the curve at that particular point in time, and then pick any 2 points on the tangent, because this is a straight line. The slope between these 2 points is the same as the slope between these 2 points. It's a straight line. You calculate the change in y with respect to the change in x, rise over run, for the tangent to a curve to get the instantaneous rate. And you can expect to have one of these on your test. All right, so let's do a quick example. Using the graph provided, determine the instantaneous rate at 100 minutes and 500 minutes. You can do these separately. So you're going to draw a tangent to the curve at the points. Select 2 points on the tangent line, determine their xy coordinates, calculate the slope of the line. So here's your solution. All right, so here is 100 minutes. We're going to draw a tangent to the curve right here at 100 minutes, and then we'll calculate the slope of that particular line. So you just pick any 2 points. So if I pick these 2 points, my difference between T2 and T1 is simply going to be 100 minutes. So this is T2 for this particular calculation, and this is T1. And so we'll have 400 minus 300. So if I'm doing this, this is going to be 400 minus 300. That's simply my delta T for this particular reaction. Okay, and then I need the change in concentration, my delta and I'm still using hydrogen ion, so I'm using the same reaction. So this is change in concentration of hydrogen ion with respect to the change in time. That would be equal. And so what we need to do now is we need to draw a straight line across there. I'm going to kind of fudge it a little bit, and I will call T1 1.25 and T2, I'm just going to kind of fudge that a little bit. It's pretty loosely drawn. I'll just call that 1.10. So this is going to be 1.10. This is the hydrogen ion concentration at times 2, and we're going to minus the hydrogen ion concentration at time 1, and at time 1 it's a little larger, and it's 1.25. Okay, this is minutes. This is molarity. Well, just capital M, guys. And remember that this is a rate of disappearance of a reactant, so there's a negative here. So that's going to be a negative. We're going to get a negative value here divided by 100 minutes, 400 minus 300. Well, I got a little ahead of myself. I'm not going to do it over, but for the first calculation at 100 minutes, you had 1.53 times 10 to the minus 3 molar per minute. That's at this particular point, okay? When I do the second calculation, remember, this is the point I'm interested in, 500 minutes. I can pick any 2 points on the curve. You can experiment with this. I could pick this point. I could pick this point. Anywhere along this curve, the slope is going to be the same, rise over run, and that's at the tangent to the curve at 500 minutes. So I went ahead and I used the numbers that I had originally determined on this particular reaction for these 2 points on the tangent to the curve, which is here we've got this is the concentration at time 1, and this is the concentration at time 2. It's a lower concentration, so concentration at times 2, 1.20 molar, minus concentration at time 1, 1.38, divided by T2, 400, minus T1, 200, and I wind up with a shallower slope, a lower instantaneous rate at 500 minutes than I had at 100 minutes, which is completely consistent with our original determination. And so this is the rate at 100 minutes, 1.53 times 10 to the minus 3 molar per minute. This is the rate at the instantaneous rate at 500 minutes, 9.00 times 10 to the minus 4 molar per minute, a lower rate. So here is a question for you. If nitrogen dioxide decreases from 0.0100 to 0.0065 molar in 100 seconds, the rate of disappearance for nitrogen dioxide for this period is, and I'll expect you to answer that question.